So our homework last night, page 453, a bunch of questions on that. We want to go over question number 7. There were no other issues with that besides number 7? Okay, number 7 it is. This is our Mexican jumping bean question. It says, Mexican jumping bean moves because an insect larva inside the shell wiggles. Would it increase the motion to have the mass of the insect greater or to have the mass of the shell greater? What's the answer to that question? How many people, let's take a little vote here. It's democracy. How many people say it would be helpful to have the mass of the insect bigger? How many people think it would be better to have the mass of the shell bigger? Most people saying the insect. That's right. Can anybody give me a reason why it would be more helpful to have the mass of the insect bigger? That is, if you want to increase the motion of things. Ollie?
Because the mass of the larva would be greater to transfer its velocity and mass with the cell, because the cell is lighter compared to the larva.
Yep. Yep. Go ahead.
The larva is like bigger, it's not just necessarily lower, like it could be like a jack larva.
Yep. Yeah. Yeah. No, here's the deal. You guys are both right. But I'll summarize it here a little bit. Give you my answer for it. So you've got two things. You've got this insect inside this shell. Okay. There's our little insect. Okay. The insect is going to have a certain amount of momentum, and it's going to transfer its momentum to the shell. And that's what's going to make the shell wiggle around. It's going to jump around, right? Now, do you want a lot of momentum to be transferred to the shell or a little bit of momentum to be transferred to the shell? A lot. If you want the shell to move around, then you want to transfer a lot of momentum to the shell. Where do you get more momentum from? An insect that has a little mass or a big mass? An insect with a big mass. So the faster this little insect is moving, the heavier this little insect is, the more momentum that this insect is going to have. Therefore, the more momentum it's going to transfer to the shell. Therefore, the faster the shell is going to move, the more it's going to wiggle around. Here's another way to think of it. Do you want to transfer a lot of momentum to something light, or do you want to transfer a little momentum to something heavy if you want that thing to move? A lot of momentum to something light, right? That's what's going to cause it to move a lot more. Make sense? All right, if there's no more questions on that, let's take a look at the worksheets, worksheet number 1 that we had for homework last night, or at least the first 5 questions that we had to do. Any issues with any of those 5 questions? Nobody had any issues with something like, say, this? Doing a question like this, draw attention to it, right? Circle kilometers per hour, because you don't want to forget to convert that to meters per second. Listen, if this is an exam or a unit test, and this is a multiple choice, you can be sure that one of the 4 options is 2,500 times 110. That's the wrong answer, but it's going to be one of the options. You're going to fill that in, you're going to bubble that in, you're going to think you got the right answer, because the answer you got is there as an option, but then you're going to have it wrong. So you're going to think you got a 90 on the test. You're going to end up with a 60 on the test because you did that three or 4 times. Right? Be careful. Be aware of that. Okay? Draw attention to things like unit conversions so that you don't make that mistake. Ethan, was your hand up there? Yep. Let's take a look at number 5 here. It says a 5-kilogram ball accelerates from rest at a rate of 2 meters per second squared for 1.5 seconds. Calculate the ball's momentum after the acceleration. This is somewhat like a couple of the questions we did, but yet not exactly the same thing as a couple of questions we did. Remember the problems where you dropped a rock or you threw a ball from a certain height, and then we wanted to find the momentum when it struck the ground? Right? This is similar to that in that you want to find the momentum after this has happened, right? The final momentum. That's what we want to do here, find the final momentum. What's different about it? Well, it's accelerating, but it's not gravity that's causing it to accelerate. Okay? We have an acceleration of 2 meters per second squared as opposed to 9.81 meters per second squared. So let's look at this. Okay? We know that it's the same type of problem except that the acceleration is different. We know our mass is 5.00 kilograms. We know that VI is 0 meters per second because it starts at rest. And we know that A is 2.00 meters per second squared. We know my time interval is 1.50 seconds. We know we want to find PF, which is m times VF, mass times the final velocity. What's VF? Don't know. How are we going to find it? How are we going to find it? I think in each of the questions that we did were somewhat like this. We used VF squared is equal to VI squared plus 2AD. Is that going to work here? Yeah, let's just use that one, the basic one. A is equal to delta V over delta T. Rearrange it. Delta V is equal to A times T. Um, 2 meters per second squared times 1.5 seconds gives me 3. Wait a second, though. Isn't that the change in velocity? I want VF, right, not delta V. How do I get VF? Rosie? Oh, okay, fair enough. Remember in Physics 20, we always talked about that, how like, there was often more than one way of getting the same thing. Okay, that's a little bit longer because it's a 2-equation method to get there, but it doesn't matter. It's the same thing, right? Okay. And that gets you VF directly, though, as opposed to delta V, so it has that benefit. Sure. Did you hand up? Okay. Yeah, you got to minus VI from VF, right? Sorry, you got to add VI to delta V to get VF, right? But the thing is, what's VI here? 0. So what's VF? Same as delta V, right? So whether you're solving for VF or delta V, doesn't really matter there. All right, let's plug that in now. M is 5 kilograms times VF is 3 meters per second. That works out to be 15.0 kilograms meters per second. Is that good? All right, I'm going to assign the rest of those questions now. If you haven't already finished them, some of you have. You know what, I'm going to give you a few minutes to work on them, actually. Not a great deal of time, probably not time to finish them, but a few minutes to get a head start on them. 6, 7, and 8 for homework for tomorrow, please. All right, up until now, we've talked about momentum, which is a quantity that exists at a specific moment in time. Now, sometimes that momentum isn't changing, so over a period of time, we can find it because it's staying the same. But what if it's changing? Sometimes we've done problems involving a changing momentum, but we've still looked at the momentum at one specific moment in time. What's the momentum of the ball as it strikes the ground as it's been thrown down from a height of 10 meters? Well, the momentum was changing, but we were looking for the momentum as it struck the ground. Or we could have found the momentum halfway down, or we could have found the momentum at the top before it was moving downwards, or whatever the case may be. How do we account, though, for the changing momentum? Not the momentum at one specific time, but the changing momentum over that period of time. Well, that's with a quantity that we know as impulse. Impulse is defined as, you can probably guess, the change in momentum experienced by an object. A car traveling down the road is moving at a certain speed. It has a certain mass. It has a certain momentum. Later on, it's going faster. It has a different momentum. There is a change in momentum between what it had and what it has. A baseball is moving out towards the outfielder. The outfielder catches the baseball. The baseball had a certain amount of momentum, and now it has no momentum. There was a change in momentum or an impulse experienced by that baseball. Impulse is the change in momentum experienced by an object. It's a vector, because of course, if momentum is a vector, then impulse, the change in momentum, also has to be a vector. Can you tell me what change in momentum might depend upon? In other words, what do you think you need to do to something to change its momentum? What do you think you got to do to change its momentum? Yep. Well, not necessarily in the opposite direction, right? Change in momentum doesn't necessarily mean decreasing. Okay, if you want to decrease momentum, then yeah, you got to push in the opposite direction. If you want to increase it, you got to push in the same direction, right? In other words, you have to apply a force, right? You got to push it or you got to pull it. You got to apply a force. Now that force has to be applied over a certain period of time, right? What do you think would affect the momentum more? Bigger force or a little force? What's going to create a bigger impulse, a bigger change in momentum? Big force, little force? Big force. What do you think is going to change the momentum more? Big time that the force is applied for or little time that the force is applied for? Apply a force for a longer period of time. Is that going to affect the impulse more or less? More. Force and time are my two big factors here. Let's derive an equation here for impulse. We're going to go back to Newton's second law, which you learned in Physics 20. Do you guys remember what that was, by the way? Yeah. Good. F is equal to m times a. Believe it or not, that's not actually the way that Newton stated his second law. Yeah, that's the way that we stated it in Physics 20. That's not the way that Newton stated it. The reason that that we stated it this way in Physics 20 is because you didn't actually know enough in Physics 20 to state it the way that Newton did. He talked about impulse, the change in momentum. We didn't know anything about momentum last year in Physics 20. So we kind of twisted it around and called that F is equal to m times a. Okay, bear with me now as I go through this. F is equal to m times a, but a is equal to delta v over delta t. Is that okay to replace a with delta v over delta t like that? Sure it is. Yep. Let's rearrange this a little bit. Take the t up by multiplying. So F times delta t becomes equal to m times delta v. What's the equation for momentum? Mass times velocity, m times v. So what do you think m times delta v would be? If mv is momentum, what do you think m times delta v would be? Peter? The change in momentum, right? The change in momentum, delta p. What do we define change in momentum as? Impulse. So impulse, we're saying delta p is equal to m times delta v, but it's also equal to f times delta t. I want you to take out your data sheets right now. Third page of your data booklet. You open it up, you're going to see under momentum and energy an equation at p is equal to m times v, but you're also going to see an equation f times delta t is equal to m times delta v. That's your impulse equation. It doesn't say delta p there. It doesn't remind you that it's impulse. They're going to trust that you remember that m times delta v is change in momentum or impulse, and therefore f times delta t is as well. This equation validates what we hypothesized just a few minutes ago, right? What are the two things that are required for there to be a change in momentum? Well, you got to apply a force and over a period of time. Force and time matter. Bigger force, bigger impulse, bigger change in momentum. Bigger time, bigger impulse, bigger change in momentum. Right? Now, I'll tell you what, we're going to use this to solve a number of problems. Look at where it came from though. F is equal to m times a. When all is said and done, there's no problem that we're going to do using impulse this year that we couldn't use F is equal to m times a for as we did it last year. In other words, any problem we do this year involving impulse, we could have done last year using F is equal to m times a. But impulse is often a more convenient way of doing it. So we're learning a new tool. We're not replacing anything. We're just adding a tool to the toolbox, a more convenient tool in some cases. When is it more convenient? When is it useful to use impulse over F is equal to m times a? Well, there's a couple of situations. Clearly, if the question asks you for impulse, right, or it asks you for the change in momentum. Or maybe it says, here's the impulse, what is the force, or whatever the case could be. But it mentions the word impulse. If you see a change in momentum, That could include a momentum gain or a momentum loss. How much momentum was gained by the car as it accelerated from rest to whatever? How much momentum was gained? Okay. What's the change in momentum of the baseball as it was caught by the outfielder? How much momentum was lost by the car as it struck the other car? Change in momentum, momentum gain, or momentum loss. The third and final one, though. If you see a force and a time in the same question, there's got to be an impulse, right? If you see a force and a time, there's got to be an impulse, a change in momentum. I'm going to star this one because this one is often the trickiest one. Clearly, if it asks for impulse, change in momentum, not much different than impulse. But force and time, sometimes we see the word force and time in the problem, and we're not even told, we don't even see the word impulse or the word momentum in the question, but yet we still use impulse to solve the question. If you see a force and a time, even if it doesn't say the word momentum or impulse, I want you to automatically think impulse. So, what are the three things? Number one, I don't care what order you give them to me. Holly? Not change of impulse. Don't say change of impulse. Asks for impulse, right? If it asks for impulse, and that's a pretty obvious one, right? If it says how much impulse, blah, 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 then you're going to use impulse to solve the question, right? Yeah. Force and time. If you see a force and time in the same question, automatically think impulse. Maybe you don't even see the word. Maybe it just says 20 newtons was applied for 10 seconds, blah, blah, blah. Doesn't have to mention the word momentum, doesn't have to mention the word impulse. And if you see a change in momentum, momentum gained, momentum lost, momentum dissipated, anything like that tells you we're going to use impulse to solve the question. Again, we could use Newton's second law, F is equal to m times a, but this, in those three situations, is generally more convenient. So that's what we're going to try. Let's take a look at an example. 9.3, page 458. Question says, to improve the safety of motorists, modern cars are built so that the front end crumples upon impact. Did you know that? Did you know that cars are built to be destroyed? You ever think, oh, wouldn't it be nice to have this rigid car that didn't crush in a crash? Like you could crash it and you could still keep using it? That's not a good thing. Okay, that's not a good thing. Crumple zones are built for safety, for your safety, not for the car. We're sacrificing the car for your safety. Okay, you'll see why in just a few moments here, why that works. 1,200 kilogram car is traveling at a constant velocity of 8 meters per second. It hits an immovable wall, comes to a complete stop in 0.25 seconds. Calculate the impulse provided to the car. Let's worry about one question at a time. Calculate the impulse provided to the car. Okay, clearly this is a what kind of question? Yep. How do you know? Forget about B and C, just look at A. How do you know this is an impulse question? Don't overanalyze here. Asks for impulse, right? If it asks for impulse. Okay, let's write down some givens. Now that we know what's going on, we know that it's an impulse question, let's write down some givens here. We got a mass here of 1,200 kilograms. We have an initial velocity of 8 meters per second to the east. We have a final velocity of what? 0. Comes to a complete stop in 0.25 seconds. Delta t is 0.25 seconds. So we want to find the impulse, bless you, delta p. Now, we have really two equations that we can use for impulse. Delta p is equal to F times t, or delta p is equal to m times delta v. Which one do you want to use? Remember, on your data sheet, it's got both, right? F times t and m times delta v. Which part of that are we going to use? Yep. Yeah, we know it's an impulse question. We know it's an impulse problem. Now we can just look at our givens and decide that it makes more sense to use m times delta v. Now, listen carefully here, okay? I don't know how many times I've seen this over the years. People solving for impulse. What do they write down for the equation? Delta p is equal to m times v. What's wrong with that? What's m times v? Momentum. That's not impulse. Impulse is the change in momentum. Be careful to write down m times delta v. Why is that really important? Why is that critical that you write down the equation properly? Don't ever write delta p is equal to m times v, ever. Why is it so important to write the equation down properly here? What are you going to do if you write down m times v? You're going to multiply m times v. What do you got to do? You got to multiply m times vf minus vi. Now in this case, because vf is 0, you'd get away with that. But if vf wasn't 0, then you'd get the wrong answer by just saying m times v. That make sense? M times delta v. 1,200 kilograms times 0 minus 8. If that was a 2 minus 8, then that would be a really, really big deal to not miss that. 1,200 times negative 8 gives me negative 9,600, which we should round at 2 digits, which is negative 9.6 times 10 to the 3 kilograms meters per second. By the way, there's another set of units that we can use for impulse now, for momentum now, I should say. Kilograms meters per second, right? Anybody see the other set of units we could use besides kilograms meters per second? Christian? Not quite. You're almost right. Not newtons. Newton seconds, newtons times seconds, because it's F times T, right? So at this point, I don't care whether you write kilograms meters per second or Newton seconds. Both are correct. They both mean exactly the same thing. Okay, B, what's the average net force exerted on the car? Hey, look. Force, time. Force, time. What kind of question is this? Impulse, how do you know? Force and time. Now, you got a couple of options here. You can say delta P is equal to F times T. Looking for force, got the time, got the impulse. Or you can go right back to the beginning and say F times T is equal to M times delta V. Kind of combine the two. What was our time? 0.25 seconds. What's it going to be? 1.92, 3.84 times 10 to the 4. Is that right? Technically, that should be 3.8 times 10 to the 4 newtons. Negative 3.8 times 10 to the 4 newtons. Why the negative? Ollie? Yep. Yeah. If it's moving to the right, the car is moving to the right in a positive direction, which way does the force need to be to slow the car down? To the left. So the force is to the left. We would say it would be negative 3.8 times 10 to the 4. Okay, that's a pretty big force. That might hurt. When you crash into a concrete wall or a brick wall, it sometimes hurts. What's one way to alleviate that, though? One way to prevent so much injury? Crumple zone, yeah. Let the car take it. Let the car take the impact. That's the crumple zone. And that's going to be what we address in question C here. Because for the same impulse, what would be the average net force exerted on the car if it had a rigid bumper and a frame that stopped in 0.040 seconds? So this one's actually going to be without the crumple zone. This one's with the crumple zone. This stops a lot quicker, right? That's the whole idea of the crumple zone. Increase the time of stopping. Make it stop slower. Make it take longer to come to a stop. If the car gets destroyed, then the car will take longer to stop. So for this one, we're going to say, once again, F is equal to delta P over delta T, which is negative 9,600 divided by 0.040 seconds. Negative 2.4 times 10 to the 5. Look at these two forces. Okay, look at these two forces here. When we had a crumple zone and it took 0.25 seconds to stop, the force was 3.8 times 10 to the 4 newtons. When we don't have a crumple zone and it stops a lot quicker, we have a force that's 10 to the 5 newtons, a force that's almost 10 times as big. Which one hurts more? This one, the green one, or the red one? Which force hurts you more, the driver? The red one, right? The bigger force hurts you more. When you're driving a car, excuse me, the impulse, there's one thing that we know for sure when you're driving a car. One thing that we know for sure, 100%, that car will stop. We don't know how it will stop. We hope that it's going to stop when you put your foot on the brake and gradually come to a stop, but you may have to slam on the brakes, or you may hit another car, or you may hit a concrete wall. We hope not, but we don't know. Okay? All we know is that your car will stop and that the impulse will be the same no matter how your car stops. Think about that. You're driving on the road with a certain momentum, you will have zero momentum soon. Whether you get zero momentum by crashing into a wall or by slowing down gradually, you will have zero momentum. Your impulse, your change in momentum will be the same. It's not impulse that hurts you. It's force that hurts you. So what do we want to do with the car? Not change the impulse. We want to spread the impulse out over a longer time. And how do we do that? How do we spread it out over a longer time? We build cars with crumple zones. We also build cars with, airbags. What's the purpose of an airbag? To increase the stopping time, which decreases the force. It does nothing to the impulse, but it increases the stopping time and decreases the force. That makes sense? We'll talk a little bit more about this later on, but this is the basic principle behind pretty much every impact cushioning thing out there, whether we're talking about an airbag or a crumple zone in a car, whether we're talking about a baseball glove that's padded a little bit. Who plays basketball here? Okay. A couple guys play basketball here. Catch a basketball. How do you catch it? Like, and just keep your arms out rigid like this? No. What do you do? What do you do when like intuitively when the ball comes towards you, you kind of cradle it, right? What are you doing? Yeah. The impulse of the ball is going to be the same no matter what. You're increasing the stopping time of the ball. What does that do? Decreases the force, which means you're more likely to be able to hold on to it if it's less force, right? When I was a kid, I remember I grew up in rural Nova Scotia. Big. My parents had a pretty big property, and there's this area beside our house that would sometimes, when the creek behind had a lot of water, and it would sometimes flood. And in Nova Scotia, growing up, wasn't nearly as cold as it is in Alberta in the wintertime. And we had these cycles, often had these cycles of like it would get cold, like -10 kind of thing, and then it would rain hard, snow would melt, and then our side yard would flood, and then it would freeze. So we'd have a rink. Most of the winter we'd have a rink that just happened. We didn't have to do anything to it except shovel it. We just have this rink. So I would play hockey outside just about every day with my brother or with my friends or whatever. And I remember one day I was outside with a neighbor across the street. His name was Derek. And I remember playing goalie. I didn't have goalie pads, but I had shin pads, like regular hockey shin pads. So I put these shin pads on. That's it. I had shin pads on and a baseball glove. That's it. No helmet, no, nothing. And I remember he's taking shots at me, and I'm, saving some of them, letting some of them in, whatever. And I said, Derek, take a slap shot. Because I thought like if it's like up at my head, I'll just get out of the way or something like this, right? So he takes a slap shot. It's low, and I go down to try to block it. And the flap that covers your knee from the shin pad flaps out, and it caught me. The slap shot caught me right on the kneecap, and it was about the most painful thing that you can imagine. But yet goalies do that all the time. Like real goaltenders with goalie pads do that all the time. How do goalie pads prevent the goaltender from being hurt like that all the time? The impulse of the puck is going to be the same. Increase the stopping time. Okay? Goalie pads increase the time that it takes the puck to stop. Now, goalie pads also spread the force out over a bigger area, over your entire shin. Okay? But one of the things is it increases the stopping time, decreases the force. My kneecap didn't do that so well. Make sense? Okay, let's have a look at these two questions, please. Page 458. All right, let's have a look at question number 2 now. It says, a dog team pulls a 400 kilogram sled that has begun to slide backward. In 4.2 seconds, the velocity of the sled changes from 0.2 meters per second to 1.8 meters per second. Calculate the net force the dog team exerts on the sled. All right, we know these are impulse questions, right, because that's the topic that we're doing, right? We're not going to see some other question right now that's not relevant to the topic that we're just doing. But if this is, let's say, I don't know, 4.5 months from now when you have an exam, a diploma exam, how do you know this is an impulse question? What tells you that this is an impulse question? What keywords or concepts? I see a force and I see a time in the same question, right? Right, here's my time and I'm looking for the force, right? We know it's impulse. Now, could you use F is equal to M times A to solve this? Yes, you could. Okay, but it would be a little bit more roundabout way. I think our new tool, impulse, is a more efficient way of solving this question. So let's write down some givens and do it here. The mass is 400 kilograms. We're going to say the time interval is 4.20 seconds. We're going to say VI is, I'm going to say negative 0.200 meters per second. VF is positive 1.8 meters per second. Now, some of you might say, calculate delta P using M times delta V and then set it equal to F times T. I'm going to just do it right off the top here. F times T is equal to M times delta V. We get 400 times VF minus VI, 1.8 minus 0.2 over 4.20 seconds. Is that right? What's wrong? Okay. Good. 1.8 minus negative 0.2. 400 times 2 is 800. 800 divided by 4.2 is 190. And we get a positive value for that. What does the positive value mean? Well, if forward was positive and backwards was negative, then we get a force that's forwards. Right? Christian? Yep. 1B says two people push a car for 3.64 seconds with this force. What's the change in velocity? Okay. For this one, we can say that what? F times delta T equals M times delta V. And we're looking for delta V. Force is 200. Time is 3.64. And the mass is, what is the mass? 1100. So do the math there, works out to be a 0.662. No, wait a second, what's going on there? Oh, wait a second here. Okay, hold on. I get 0.662 meters per second. So I'm thinking right away that's to the north, right? But it's to the south. They tell me it's to the south. What have I done here? I made the 200 positive. What do they say 200 was? 200 to the south? So basically, I defined south as positive when I did that question. Right? Make sense? Notice, is that okay? Anything else there, guys? Okay, here's what I'd like you to do now then. Take a look at worksheet number 2 for a little while.